Section 2.9, I was going to build off of what 2.8 had to talk about, but instead of referring to them as equations and inequalities, we're going to look more at talking about absolute value functions. Now, again, remember, we basically said the easiest way to kind of talk about what we were saying as far as the difference between a function and an equation is the simple fact that a function meets specific guidelines to the point where we can take an equation and call it a function. And more or less, we're just replacing y with function notation, usually something along the lines of f of x or g of x or something of that nature. Now, this section should go very closely with section 2.6, which we talked about earlier in the year, in the fact that we're just taking functions. Before it was linear functions, now they're absolute value functions, and we're transforming them and translating them based on information that we're given. Moving things up and down, reflecting things across the x and the y axis, or even stretching and compressing things both vertically and horizontally. So if you can remember your rules for how all that stuff's supposed to work, this is going to be a lot easier. Now, before we get into that, the first thing we're going to specifically have to talk about is what the graph of an absolute value function looks like. Now, we should all be pretty familiar with the concept of absolute value in terms of absolute value always has to give you a positive output. Okay, there's no such thing as a negative distance. So any type of output that you get from an absolute value function is going to be a positive number, and that directly results in the type of graph that we're going to be looking at, which is a little bit different than some of the graphs we've looked at before. Alright, so absolute value functions, which I already talked about a little bit, getting into that whole function notation idea, we're going to be looking at something similar to this, and f of x equals the absolute value of x would be referred to as the parent function for absolute value functions in general. And basically what that means is, unless we're applying a stretch or compression, any other translation that we do, whether it's a reflection or a translation left, right, up, or down, is going to take this very graph, the same dimensions of that graph, and it's basically just going to move it around on your coordinate plane. The other thing we need to talk about is the fact that when you graph these, because we said that an absolute value function is always going to give you a positive output, we need to talk about the fact that your graph isn't necessarily, well, I shouldn't say necessarily, is not going to look like a line anymore. We're going to end up with something that looks like a V. Okay, so if that's the case, we're kind of going to jump right into this here. And the other thing I should mention real quick here is the parent function, the vertex, okay, or the bottom point. In some cases it can be the top point, but in this case the bottom point of your parent function, which we already talked about up here, is going to be at 0, 0. Now, it is possible to get a V that is upside down and you would have the vertex point on the top, but again, that is going to be the result of applying translations to things. So I shouldn't say that you can't ever get a negative output value out of something. You're never going to get a negative output value out of your parent function. Alright, because again, absolute values cannot be negative, and if that's the only thing present up there, that's going to be the case. But when we start adding numbers behind the function, subtracting numbers behind the function, or reflecting, then because we've altered it, it is possible to get a negative output value. But all that being said, remember, absolute value, if it's just an absolute value like we have right here, it's going to be a positive output value. Alright, now this gives us a pretty good idea of what the parent function for f of x equals the absolute value of x is going to look like, and that would be graphed up here on the right side of the screen. Now, the thing that you'll notice is obviously the v to begin with, but again, the same idea of as we move over here towards the negative x-axis, if I take values like -1, -2, -3, and I'm filling those in, you can see how I'm getting a positive output value. Or in other words, if I fill in -2, the absolute value of -2 is +2, which is why I have 2 is my output value right there. Okay. Again, unless we are actually performing a stretch or a compression, all of our translations, whether we move left, right, up, down, reflect, it's going to be a graph that looks exactly like this. All right, we're just going to be moving it around the coordinate plane. All right, now when we start applying stretches and compressions and all that stuff, then it becomes a little bit different story. Okay, and we'll get to that as we move forward. Right now, rules for translations. Remember, we talked about these before. If we're going to perform a vertical translation or move something up and down, we are going to add or subtract that number from the entire function. All right, if we're going to move things horizontally, translate them horizontally, left or right. All right, that number has to go in or be filled in with our input value along with the x. And we talked about how that's backwards. If I want to move something to the right, so many units, it's going to be minus however that is. So like if I want to move 3 to the right, it would be -3 that goes in with the x that we would have to fill in. If I want to move something to the left 3, it would be x plus 3 that gets filled in, or we're evaluating the function for that particular value. All right, so perform the translation and graph. Again, the next slide here is going to give a better idea of what the graph looks like, better than what I could graph. Now, if you weren't 100% sure what your graph is supposed to look like, again, the easiest way is to pick values of x, fill them in, and get output values so you have points that you can use to graph this. All right, so transformation to f of x equals the absolute value of x. We want to move 5 units down. Now remember, vertical translations, we are taking f of x and we are performing the translation to the whole function. So in other words, I'm taking -5 and I'm subtracting it from the entire function. So if I have the absolute value of x and I'm going to subtract 5 from that, essentially this is what I get. All right, not much is going to change. All right, so we would call that new function g of x, just simply to give it a different name. And this would be our new function, which would take the parent function, which is f of x equals the absolute value of x, and it would slide it 5 units down. What you will notice here as we move towards the actual graph of this is the dimensions of your graph have not changed. All right, if you think about it, this is my original. Basically, this side goes up 1 over 1, up 1 over 1, up 1 over 1, and it's reflected on the other side, up 1, back 1, up 1, back 1. All right, same thing down here. Essentially, the slope of each side of my v is the same, 1 and -1 if we think about going off to the left. So the dimensions of my graph haven't changed. You can just see how my starting point, which we said the vertex for the parent function is always 0, 0, and we just moved it 5 units down. All right, so essentially we've just cut a value of 5 off of every output value. Okay, so graph it, you think about it that way. The other way I like to think about absolute values if you're graphing them is out in front of the absolute value here, technically there's a 1 there in this case. Well, that represents the slope of my positive side of my graph. Like over here, this side of my graph has a slope of +1 because there's technically a 1 out in front of the absolute value, just like y equals mx plus b form, except for this time around we have a absolute value sign that happens to be in there. All right, and because absolute value graphs are symmetrical, the other side of my graph is going to be the same distance away from the y-axis. So if I know that this number out here represents the slope of the positive side of my graph, okay, or the positive x side of my graph, I could go up 1 over 1 to find the points that happen to be on that side, and then I could just count how far those happen to be away from the y-axis, in this case 4, and I could go over 4 and plot my other half, okay, because it's a reflection. That's another way you can graph if you don't want to fill in different points for everything. Okay, here we're looking at a horizontal translation. So in this case, I want to go 1 unit left. So remember, it's backwards. So I'm going to actually fill x plus 1 in for my function. So in this case, In place of the x, I would put x plus 1. All right, and there was nothing behind it to begin with. So you can see, again, it hasn't really changed a lot. And the number that's out in front here, again, is still technically at 1. So the slope of the right side of my graph is still going to be 1. So again, when we look at this, and I should probably clarify too here just at the end, that we'll just name this new function g of x so we can see that it's different. All right, but what you'll see is you have the exact same graph. It's just shifted 1 unit to the left. All right, or the vertex of my parent function, which is 0, 0, has now shifted this way. So you can see how, adding or subtracting a number from the x inside the absolute value portion of your function, like we did up here, we added 1, actually moves it back 1 to the left, or vertex 1 to the left. If we were to take, and like we said before, and add some number behind it, like in the case of this 6, all right, that moves our graph or our vertex directly up or down. In that case, it would be 6 units up. All right, and you can see in the case of g of x, which is graphed on here, my new vertex, because I shifted 1 unit to the left, happens to be -1, 0. So that's pretty much going to be the next thing that we talk about. If we take and we apply different horizontal or vertical translations to our parent function, it essentially shifts our vertex point. Okay, remember, the vertex point of this, our parent function, is 0, 0. If we shift to the left or shift to the right, that affects the x value of our vertex. If we shift up or down, that affects the y value of my vertex. So down here is what we refer to as kind of the standard form for figuring out the vertex of a absolute value equation or function. All right, the h and the k represent the coordinates of your vertex. Okay, h being the x value of your vertex, k being the y value. Now, a lot of people always ask, how come you use h and k? Well, it's because x and technically y are really kind of already taken, so we don't want to use the same variables to represent something completely different, because then we get super confused about what's going on. The important thing to remember inside is if you are given a function, inside the absolute value sign, something like this, remember the x coordinate of your vertex is kind of, think about it as being opposite of what's shown here. It says a +2 here, so the x coordinate of my vertex would actually be a -2, okay, because there's a negative sign in the standard form up here. So the opposite of that. All right, the number behind your y value of your vertex is always as is. If it's minus something, then it's a minus for your y value. If it's a plus something, then it's a plus for your y value. Okay, so we want to translate this particular function, our parent function, so that the vertex is at -1, -3, or essentially we want to move it 1 to the left and we want to move it down 3. So if we think about what was just shown on the last slide, and I'll write that up here again, our standard form for our vertex, or determining our vertex. Okay, we said it's kind of opposite as far as moving left and right. If I wanted to go 1 to the right, I would just put 1 right in here, -1. But because we want to go to the left, all right, and I'm going to just represent this with something other than f of x. All right, but because we want to go 1 to the left, we'd actually go x plus 1 because it's backwards, like it has been backwards all along, and then we want to go down 3. Okay, so in that case, that represents a absolute value function that has a vertex of -1, -3. All right, and again, on the next slide here, we graph it. Again, your parent function is in blue. The one that we just came up with, which is shown up here on this particular slide, is the same exact dimensions of that graph. It's just shifted down 3 units and 1 unit to the left, which explains why we have a new vertex of -1, -3. Okay, reflections can be applied just like they were before. Excuse me. If you are reflecting across the x-axis, essentially we're changing y values, so we just take the entire function and we make everything in it negative. Okay. At the same time, if we are reflecting across the y-axis, we're going to go ahead and change the input value because it's our x's that are changing. All right, and we would go ahead and make the x value negative. All right. So if we go ahead and look at something like this, okay, we want to reflect the graph across the y-axis. All right. So if I reflect across the y, again, I'm changing my x value. So I would have to find f of negative x. All right, which in this case would mean I would fill in negative x, and I'll put it in parentheses, meaning that's what I filled in place of the x. So you can see there's not really much that's going to change about this. All right, well, I'll call my new function g of x, but I have negative x minus 2 plus 3. Okay, now again, the number out in front here hasn't changed, meaning I haven't altered the dimensions of my graph. I've just taken it and I've kind of reflected it. Okay, so essentially what's happening here is my vertex is going to shift a little bit, all right, but my reflection is of the same graph. I just moved it from its original starting point over here to something that's over here. Or if you think about it, the vertex of my original was 2, 3. Because I changed x values by filling negative x in for x, I just moved my vertex to negative 2 instead of positive 2, and everything else remains the same about my graph. Okay, again, we're essentially still going up and over, and that graph didn't necessarily translate when I put it on there very well. Technically, this should be up 1 over 1, so I kind of ran out of my graph, didn't, I guess, show up the way that I wanted it to on there. But the whole idea is my dimensions of my v, or my absolute value graph, haven't changed. All right, I haven't actually changed what the graph itself is going to look like. Okay, now if we want to, I guess we didn't have another one in there as far as reflecting. Reflecting, if we were going to reflect across the x-axis, that would have just involved making the entire function negative. Now, if I go back here a second to the slide before, say we did want to take something and reflect it across the x-axis, or essentially bring it down. If we start with that same idea that I had, f of x of, and this would have been my original, x minus 2 plus 3. If we wanted to reflect that across the x-axis, or essentially take my y values and make them negative, I would have taken negative f of x. Now, the thing you got to be careful of with this is the fact that you are making everything on this side negative, but you don't distribute a negative into the absolute value. So if I wanted to make, this whole side negative, all right, obviously the most I could do would be write negative out in front of the absolute value sign, and then I can still make the 3 behind it negative. All right, essentially I've done the same thing as I talked about. I've made the entire function negative, or multiplied both this and this by negative. But you have to remember, like I said, you can't take and distribute a negative into the absolute value. That's why if we were taking and reflecting this, like I said, across the x-axis, making the entire function negative, we just leave the negative out front of the absolute value sign, because what would happen anyway is if we were filling numbers in for x, once we figured out what was in this absolute value here, we would then make it negative afterwards. So it would essentially take care of itself. But just remember, you cannot distribute a negative into an absolute value. Right, now back to the whole stretching, compressing thing that I talked about a little bit at the beginning here. This is the stuff that's going to change, basically the width of your v, how wide or how narrow your graph of your absolute value function, which is a v, is going to look like. Now again, vertical compressions and stuff are pretty easy. Okay, my factor is 2 here, so I'm essentially going to take that vertical factor and I'm going to multiply it by the entire function. So I'm going to take 2 times everything. Okay, kind of like the last one when I was taking a negative times everything when I was talking about reflecting over the x-axis. Here we're going to multiply everything by 2. Okay, now again, you have to remember, and we'll call my new function g of x, you can't distribute into an absolute value. Alright, so I would have to write this as 2x minus, 2 times the absolute value of x. minus 2. Okay? Can't distribute into it. You can write the multiplication like I just did, but you still cannot move operations into an absolute value. All right, so this would be my vertical stretch in this case by a factor of 2. And essentially what it's going to do is it's going to take my v and it's going to narrow it up and make it pull it away from the x-axis. Now as you can see, the number in front of my absolute value changed this time. Before it had always been a 1. Now it's a 2, and essentially what that means is the slope of the right side of my absolute value equation is now gone up, or it is 2 over 1. Alright, so you can see how that makes things a little bit steeper. And the other side of my graph is just a reflection of that. It would actually be up 2 and back 1. Alright, but you can see how this number can be used to represent the slopes of the side of your graph. Okay, and you can see how we did alter this number back here a little bit, so my vertex has actually moved down some as well. It hasn't moved left and right because there was nothing inside the absolute value of the x. Alright, but it did move down a little bit because our stretch affects our y value. Alright, and the last one that we have here would be if we compress something horizontally or stretch something horizontally. Remember, we have to figure out what our factor is, and we would be taking f of 1 over whatever our factor is times x, and that's what we'll be filling in. All right, well, you can see 1 divided by 1/2, and I know some of us struggle with this a little bit, but would be 2. So essentially what I'm doing is f of 2x. So wherever there's an x, I'm going to fill in a 2x. Okay, so if I look over here at the function I'm given to start with, all right, in place of the x, I'm going to put 2x plus 2 minus 1. So you can really see when things are all said and done, I really haven't changed a whole lot. We just kind of filled something in place of the x. All right, so it's going to affect the way things are going to look horizontally a little bit. And again, this is probably one of them that's a little bit harder to picture in your head, just because we're talking about manipulating input values as opposed to output values. But you can see with what we got up here, when we compare it to what we originally had, even though the only difference is this 2 right here, you can see how it really takes things and narrows them up a little bit. All right, because we're going to, again, impact the x values that we happen to fill in. All right, you can see though that these numbers back here, nothing affected our vertex, so we're still at -2, -1. All right, so most times those horizontal stretches and compressions are not going to affect our input values a whole lot as far as what our x is. Now it does have the potential to move it left and right. Had there been something other than 2x that got filled in, you know, it could have affected the 2, but more times than not, you're not going to move your vertex a whole lot on horizontal stretches and compressions. Vertical, however, if you happen to affect this number back here, it could move it up and down. Now, it's probably not something that you really have to worry about a whole lot, because you'll be able to see the result of that based on the numbers that you come up with at the end. Okay, so hopefully this should be, you know, relatively easy, just because, like I talked about before, it's one of those things where it's very similar to the translations and transformations that we performed with linear functions. As long as you get the general idea of what an absolute value graph is supposed to look like, you should be okay with this. Again, hopefully you took some notes throughout this, kind of help you out along your way. There are additional notes and examples that are posted for your viewing. Otherwise, if you have questions, please make sure you ask.